Graphite, one of the most valuable industrial minerals, plays a crucial role in batteries, lubricants, refractories, and emerging technologies like electric vehicles. In Sri Lanka, graphite mining has a long history, but the sorting process remains largely manual. At many plants, workers separate graphite lumps by hand at curing tables, relying on visual appearance and texture. Experienced workers can estimate quality. Manual sorting is slow, subjective, and inconsistent. Human judgment often leads to variations in the carbon percentage, directly affecting product quality and processing efficiency. As demand for high-purity graphite increases globally, the need for a more precise, faster, and data-driven method has become essential. Recognizing this challenge, our project, Graphite Sorting Based on Carbon Percentage Using AI, aims to develop an automated system capable of classifying graphite based on its carbon content using advanced image processing and machine learning. Our motivation stems from two core ideas. First, to improve accuracy and reliability in graphite grading, ensuring consistent quality for export and industrial use. Second, to reduce dependency on manual labor, creating a safer and more efficient working environment inside graphite processing plants. We propose a computer vision-based sorting system that captures images of graphite samples, analyzes their surface texture, and predicts their carbon percentage class automatically. The overall process begins with image acquisition. High-resolution images of graphite samples are captured under controlled lighting conditions. Next, these images are processed to extract meaningful features that describe texture and reflectivity, both of which correlate strongly with the carbon content in graphite. By integrating these features into a machine learning model, the system learns to distinguish between different graphite grades such as high carbon, medium carbon, and low carbon samples. This automated approach not only improves accuracy, but also opens the door to real-time sorting in industrial plants. Dataset consisted of images collected from graphite sorting areas, representing four main types of lumps as BL9799, BL9092, BL6065, and rocks. Each image underwent several pre-processing steps: conversion to grayscale to simplify analysis, noise reduction using filters, and cropping and resizing to maintain uniform dimensions. We then used the gray-level co-occurrence matrix, GLCM, to extract texture features such as contrast, correlation, energy, and homogeneity. These features provide a statistical representation of how pixel intensities are distributed, effectively quantifying surface texture that the human eye uses intuitively. The extracted data formed the foundation for our classification model. Several machine learning algorithms were tested during model development. Among them, the random forest, RF, classifier combined with GLCN features delivered the most stable and accurate results. The random forest model works by creating multiple decision trees, each trained on random subsets of the data and averaging their predictions. This approach reduces overfitting and increases generalization, making it highly suitable for visual texture classification. We compared the GLCM plus RF model with alternative approaches, including YOLO, which was tested as a challenge for object detection in real-time environments. While YOLO performed well for object identification, the random forest model provided higher classification accuracy for texture-based carbon differentiation. The final system was trained and validated using our labeled dataset, and model performance was evaluated using accuracy metrics and confusion matrices. LCM plus random forest model achieved excellent classification results, demonstrating strong capability in identifying graphite samples according to their carbon percentage. Key observations from our results include: the model showed high accuracy in distinguishing between high carbon and low carbon samples. Misclassifications were minimal, mostly between medium grade and high grade categories where visual differences are subtle. Feature importance analysis revealed that contrast and homogeneity were the most influential texture features for accurate prediction. These outcomes confirm that our AI-based approach can effectively replicate and even surpass human judgment in graphite sorting tasks. The developed system offers multiple practical advantages: accuracy and consistency. Automated classification eliminates subjective human bias, providing uniform sorting results. Speed and efficiency. AI processing can evaluate dozens of samples per second, significantly increasing plant throughput. Labor reduction. Reduces the physical strain and occupational risk faced by workers performing manual sorting. Scalability. The model can be extended to other minerals or quality assessment tasks with similar optical characteristics. Cost effectiveness. Once trained, the system requires minimal maintenance and can run continuously with low operational cost. Overall, this design supports a shift towards smarter, safer, and more sustainable mineral processing. For future work, several enhancements are planned, integrating real-time video capture and YOLO detection to perform on-the-spot sorting along conveyor belts, expanding the dataset with samples from different mines and lighting conditions to improve model robustness, incorporating hardware implementation such as embedded cameras and microcontrollers to deploy the system directly within graphite processing plants, linking the AI system with industrial automation lines, allowing automatic separation of graphite grades based on predicted carbon content. These developments would bring us closer to a fully autonomous graphite sorting plant powered by artificial intelligence. For future work, several enhancements are planned, integrating real-time video capture and YOLO detection to perform on-the-spot sorting along conveyor belts, expanding the dataset with samples from different mines and lighting conditions to improve model robustness, incorporating hardware implementation such as embedded cameras and microcontrollers to deploy the system directly within graphite processing plants, linking the AI system with industrial automation lines, allowing automatic separation of graphite grades based on predicted carbon content. These developments would bring us closer to a fully autonomous graphite sorting plant